All right. Hello, IB physics students. Um, hey, make sure you guys check out the news for today's date because there's some pretty big news from IB regarding your exams. Check that out if you haven't already. Um, and hello to all three of you who are watching. Um, I'm sitting here in a cloud of Hazel's farts. Um, I'll show you where she is. She's right down here, and she's farting continuously. So I'm dealing with that right now. Life is hard. Hello, Charlie, Rourke, Nihar, Galen. Welcome. So first thing I wanted, this should be a pretty easy lesson. So the first thing I wanted to talk about was how do we know the nuclear model is correct? And basically what we did, or what scientists did, was they did this experiment. It's a pretty famous experiment. Depending on who you ask, this experiment is either called the Geiger Marsden experiment, or it's also called the Rutherford experiment. And you can ask your theory of knowledge teacher about this because it's kind of interesting. So Rutherford was the principal investigator. Okay, he was the guy who was running the lab, and Geiger and Marsden were his graduate students. And so Rutherford conceived of the experiment that I'm about to tell you about, and Geiger and Marsden actually did the experiment. So some people call it the Rutherford experiment. Some people call it the Geiger-Marsden experiment. So who should get more credit? Should it be the person who conceived of the experiment or the people who did the experiment? I don't know. I don't know why we can't just call it the Rutherford Geiger-Marsden experiment, but whatever. And so here's the experiment. Okay. They had some gold foil. And the gold foil was literally, they pounded the gold foil with a hammer. Oh, they didn't use a hammer, but somehow they got it super thin so that it is literally one atom thick. Okay? Literally one atom thick. Okay? And they launched what are called alpha particles. So here's an alpha particle gun. Okay, which is blasting alphas. And I'm not going to explain what an alpha particle is right this instant, but I will later in this lesson. But it's just a little particle, okay? And so they're blasting alpha particles at the gold foil. And here's what they observed. They observed that most of the alphas just went straight through. And so what that told people, or what that told the scientists, is that the atom is mostly empty space. Okay? So that electron cloud is very diffuse. Okay? It's not very dense, and the alpha particle just plowed through the electron cloud. So it told them that the atom is mostly empty. Okay? Some of the alpha particles hit the gold foil and were just completely reflected back in the opposite direction. Okay? And so these were the ones, some alphas hit the nucleus. Okay? And those alphas that hit the nucleus, now an alpha particle actually has positive charge. So what that means, and then the nucleus, you recall, has positive charge. And so as the alpha particle comes up, it's repelled by the nucleus and it gets sent back in the opposite direction. So the fact that some of the alphas hit the nucleus and just completely reversed their direction, that was indicative of a nucleus that has highly concentrated positive charge. Okay? And not very many of the alpha particles were sort of like mildly deflected. Okay? So this told them that the atom is mostly empty space and that there's a high concentration of positive charge in the center. Okay? So what is an alpha particle, by the way? An alpha particle is a type of radiation. Okay? So let me tell you about the different types of radiation. Okay? So this is kind of the second part of this lesson. All right? So I got a good question from Akshay about what happens if the alpha hits an electron. Electrons are much less massive than the alpha particle. So the electrons are, they cause sort of minor deviations in the path of the alpha particle, but they're not heavy enough to really truly change the path of the alpha particle. So an alpha particle is a helium nucleus, which is built up out of 2 protons and 2 neutrons. Okay? So 2 protons and 2 neutrons. So what that means is that it has a charge of +2. Okay? So because it has 2 protons. And when I say +2, I mean +2 times 1.6 times 10 to the minus 19 coulombs. But when we're talking about nuclear physics, we can just say +2. So that is one type of radiation. Another type of radiation is what's called a beta particle. And a beta particle can either be positive or negative in charge. And what it is it's an electron or an electron's what's called its antiparticle, which is a positron. So we'll learn more about antiparticles this week and next week. But basically a positron is the exact same thing as an electron, but it has a charge of +1 instead of -1. Okay? So an electron has a charge of -1. A positron has a charge of +1. Now, and it turns out that a beta particle is really light. It's super light. Okay? An alpha particle is about roughly 8,000 times as heavy as a beta particle. So there's the question of why doesn't the alpha particle, what happens if it hits an electron? Well, the alpha particle, if you were to hit something that was 8,000 times lighter than you, I don't even think you would notice. So the alpha particle doesn't notice that much when it hits a something. Okay, and then the third type of radiation is something called a gamma particle, which is just a photon. Okay. Which, if you recall from Friday's lesson, is a particle of light. So a photon actually has mass 0. And it also has charge 0. Christian asks the question, what about the speed of the lighter particle? And yeah, so because beta particles are lighter, they tend to have a higher speed. Okay? So alpha particles are kind of heavy, slow, and beta particles are light and fast. Gamma particles, they're light, so they move at the fastest possible speed. They move at the speed of light. So which ones of these are the most dangerous? Okay. Hey, Michael. Which one of these are the most dangerous? The most dangerous is definitely the gamma ray. Why is the gamma ray the most dangerous? Because it has no net charge, no charge, it is able to pass through things very easily. Okay? So if there's a source of gamma radiation, that gamma radiation is going to pass directly through your body. Okay? And so some of those gamma particles are going to hit your body and mess up your DNA, which can cause cancer. It can damage cells, etc. Okay? So gamma particles are most dangerous for that reason. Alpha and beta particles, because they have electric charge, that means that they can feel the electrical force and get sort of bent off course, more so than the gamma particle. And so for that reason, alpha and beta particles can be blocked fairly easily. Okay? So for example, if you had an alpha emitter, you could take this alpha particle gun and point it at your body, and you're not going to have any danger of getting cancer because your skin can block alpha particles. Okay? Your skin can block beta particles. Even the air itself can block many of these particles. So, yeah, the danger is eating something accidentally that is emitting alpha particles or beta particles, because then you don't have your skin blocking the stuff from getting in. You're being irradiated from the inside. Question, is the gamma particle going to be attracted to anything? It has no charge, so no, it's not. Basically, it's only going to interact with something if there's a direct hit with something. Okay? So what emits these different types of radiation? What emits radiation? And basically the answer to that question is unstable nuclei. So the way that nature works is things that are unstable try to become more stable, okay? So basically you have an unstable nucleus, which is called a parent nucleus. Parent as in like mother or father, okay? You have a parent nucleus, which is unstable. So I'm putting little lines for vibrations, okay? It's an unstable nucleus, okay? And then in the process of becoming more stable, it spits out radiation. So radiation gets spit out, and the radiation will actually tend to change the identity of the nucleus, so it'll go from one element to another. We'll talk about that tomorrow. But this is called the daughter nucleus, which is not necessarily stable, but more stable than the parent. Okay, so I'll put more stable. Okay, so what if you had a sample of unstable nuclei? So you have a sample of unstable nuclei. Well, what's going to happen is that sample of unstable nuclei is going to slowly transform into stable nuclei. Okay? So maybe this is 100% unstable. So it's spitting off radiation. It starts spitting off radiation. And after a while, you're going to have 50% unstable, and you're going to have 50% stable. All right? So what happens is basically slowly the amount of unstable nuclei goes down and the amount of stable nuclei goes up. Okay? And the time it takes for this to happen, for you to go to 50% stable, is called the half-life. Which is denoted of unstable nuclei with half-life equal to 2 years. Okay? How much unstable nuclei remain after 10 years? So how many half-lives would 10 years be? Well, a single half-life is 2 years. So 10 years is going to be 5 half-lives. By the way, another symbol for half-life is lambda. Who knows? I'm back. So yeah, I was saying that lambda is also a symbol for half-life if you've ever played the video game, the computer game Half-Life. So 10 years in this example would be 5 lambda, 5 half-lives. So every half-life you divide the amount of unstable nuclei by 2. So the amount remaining would be 95 divided by 2 to the 5th power because it was 5 half-lives. Okay, so if I do that with my calculator, 5 divided by 2 to the 5th is 2.97 grams of unstable nuclei would be remaining. Okay? You can also get the half-life from a graph. The graph is a graph of what's called activity versus time. So activity is a word for the amount of radioactivity, that is the amount of radioactive particles that's coming off of a sample. And activity is measured in decays per second. So it's the decay rate. Okay? And what is observed, so you have this exponential decay in the amount of activity as time goes on. You start off with a certain amount of activity, let's call that just 1. And after a certain amount of time, the activity goes to 0.5, half the activity. So the amount of time it takes to go to half the original activity is the half-life. So you can graphically determine the half-life. Okay? Now, things that have, there are nuclei that have extremely long half-lives, like billions of years. If something has a half-life of billions of years, that means it stays radioactive for a very long time. But that means that it's also pretty slow. It's not very active. You get what I'm saying? If something that has a really short half-life is going to give all of its radiation away in a quick burst, okay? But something with a long half-life, it's going to be a slow burn of radioactivity for a long time, okay? So this does longer half-life mean more stability? That's a really good question. I don't know. It depends on how you define stability. If you define stability as simply, the time it takes to decay, then I would say yes, it's more stable. But this freaking thing is pissing me off. Yeah, so, but then you could also have things that release a lot of energy. So there's also it kind of depends on the amount of energy released by the radiation and how long it takes. I was going to say, if you have